Hello, students. I started writing this out because this next argument is going to be kind of long. This is going to be one of those proofs that has, the following or equivalent. So we have a whole bunch of different things that are all equivalent to each other. So let's start off. 1. So V is a finite dimensional vector space. T is going from V to V. It has the distinct eigenvalues, lambda 1 through lambda n. These are all the eigenvalues. Okay, this is our when we start. And if this is the case, then we have the following, or I'll do A. T is diagonalizable. Okay. B is that V has a basis of eigenvectors. Sorry. For T, of course, because we only have one transformation. So it's going to be eigenvectors for T. C. There exist one-dimensional subspaces. And not necessarily relating, I'm not thinking about the eigenvalues when I write this, but I do want them to be invariant. So I'm not mentioning which eigenvalues when I write this part under T. So that V is going to be the direct sum. D is going to be that V is going to be the direct sum of the eigenspaces. And then finally, just that the dimensions add up. So that the dimension of V happens to be equal to the dimension of, well, I could write it like this. The sum of all the dimensions over I, from I to 1 to n. Okay, so let's see what this is saying. If V is finite dimensional and T is an operator with eigenvalues lambda 1 through lambda m, these are all the eigenvalues. This is important because, you don't want to just take some there. Then this wouldn't work out. We wouldn't have enough for this part if we were taking a partial collection of the eigenvalues. Okay, then the following are equivalent. T is diagonalizable. It has a basis of eigenvectors. There exist one-dimensional subspaces that are invariant under T, so that V is the direct sum of those subspaces. V is the direct sum of the eigenspaces, and that this dimension, the dimension of V, equals the sum of the dimensions of the eigenspaces. Now, these last two parts may look familiar. We had this in the section earlier when we did not assume diagonalizability, right? So what's going on here? Well, here, in the previous argument, what we said is that this has to be less than V. And we said that this was a direct sum inside V, but we didn't say that this was a direct sum that equals V. And in that argument, we could use a subset of the eigenvalues. But here, we're assuming T has the distinct eigenvalues lambda 1 through lambda m exactly. These are all the eigenvalues. Maybe I should add exactly. So these are all of them, not just a subset of the eigenvalues. These are all of the eigenvalues. Okay, so how are we going to prove this? Well, we'll start from the top. Some of these look like they're easier to connect. A and B, sort of, if you have a basis for eigenvectors, it's going to be diagonalizable. We sort of have already seen that. These two are certainly connected, right? Because we know, we know that if this is a direct sum equal to V, and I add up the dimensions of these, they have to be V. we could just pick a basis inside each one of these, and they form a basis for V because this is direct sum, and then this is going to follow. So D and E, closely connected. A and B, closely connected. So the challenge here is going to be to get between these two, which are connected, these two, and this. So we basically have these three main things, even though there's 5 of them, but we have these 3 main things. Okay, because there's a lot on the table. It's physically on the table, so I can say that. Yeah, a lot on the table here. Let's actually start the proof of this in the next video.